Music separation research has been focused on separating instruments for karaoke-like applications, restricted to vocals, bass, and drum separation from pop songs. This is aided by the very popular MuseDB dataset, which contains the ground truth for only these specific stems. This has resulted in gaps towards more specific music separation tasks outside of pop music, like separating choirs or string sections. In our work, we explored the task of monotimbral source separation in the context of choral music. Our first challenge was to prove that time domain separation with permutation invariant training indeed does work successfully for monotimbral mixtures. Typical approaches to solve this task have often utilized the score information of the musical piece for an informed class-based source separation. We tested a non-informed force-source a cappella separation model based on a modified dual-part transformer model with PIT trained at 22.05 kHz sampling rate. This allows the model to separate any four vocalists singing at the same time, regardless of their vocal register, unlike the other separation models which were presented in previous research. While training our models, we saw that randomizing training mixtures, that is to select parts of different songs to generate an artificial training example, ends up significantly hurting our model's performance. This was surprising as random mixing has been a well-reported augmentation technique used in the common music separation task. Although it makes sense why training with musically incoherent random mixtures sounds like a bad idea, we wanted to scientifically show why this indeed doesn't work for choral mixtures. We introduced a measure for harmonic complexity called Harmonic Overlap, which says how difficult it is to separate any two notes being played together. For example, two people singing an octave apart are likely more difficult to separate than two people singing a third or a fifth interval. We show that our model in fact does perform poorer for examples that have higher harmonic overlap. This also supports our finding where randomizing mixtures during training negatively affected performance, since randomizing mixtures destroys the harmonic overlap between the sources. We achieve very good results as compared to the existing literature, although fair comparisons are difficult since the other models were trained and tested on different datasets. Here is an example. And here is one of the outputs from our model. We find that time domain separation with permutation invariant training is indeed successful at separating vocal harmonies at high sampling rates. We also conclude that preserving musical integrity in training data for vocal harmony separation is crucial, as harmonic overlap indeed makes vocal harmony separation a different task from the speech or music separation task.